This Bitcoin address spells love. Generating it took about a minute of computer time. A similar address spelling love peace would take longer than humans have existed. Today, we'll unpack how Bitcoin keys are formatted, why vanity addresses are a mathematical vanity project, and why that paper wallet in your drawer is a ticking time bomb. A Bitcoin private key is just a 256-bit number, nothing more. But that single number wears different costumes depending on where it lives. In memory, it's raw binary. In documentation, it's hexadecimal. When you export it from a wallet, it gets dressed up in a format called WIF, wallet import format, or its cousin, WIF-compressed, same key, 4 outfits. The format you see tells you nothing about the key's strength, only about how it's being transported between wallets. Let's build WIF from scratch. Take the raw 256-bit key, prepend a version byte, 0x80, and that marks it as a Bitcoin private key. Append a 4-byte checksum, computed by hashing the result twice with SHA-256 and taking the first 4 bytes. That checksum catches typos, encode the whole package in base 58 check, an alphabet that excludes lookalike characters like 0 and capital O. The output always begins with the character 5. So anytime you see a key starting with 5, you're looking at a WIF-encoded private key destined for uncompressed public keys. Now the compressed variant, same version byte, same key, but insert 1 extra byte, 0x01, right before the checksum. Encode again with base 58 check, and the output now starts with K or L. Despite the name, the private key isn't compressed. It's actually 1 byte longer. And the 001 is a flag. It tells the importing wallet to derive compressed public keys from this private key and scan the blockchain for the corresponding addresses. And the compression happens on the public side, not the private side. Here's the intuition. Go from 99 to 100 in decimal. You added 1 digit, and the leading digit flipped from 9 to 1. Base 58 behaves the same way. Add 1 byte to the payload, and the leading character shifts from 5 to K or L. That's the entire mystery. A quick misconception to bury. Compressed private keys are not smaller, they're 1 byte longer. Compressed refers to the public keys derived from them, never the private key itself. Now the fun part. A vanity address is a valid Bitcoin address containing human-readable letters, like that love address from the opening. How do you make one? Brute force, generate a random private key, derive its address, check whether the address starts with your desired pattern. If not, throw it away and try again, millions of times, same elliptic curve, same cryptographic hash, same security as any other address. The pattern is cosmetic. Nothing about vanity addresses makes them stronger, only slower to produce. Here's where vanity addresses hit a wall. Every extra character you demand multiplies the search by 58, the size of the base 58 alphabet. Meet Eugenia. She runs a children's charity and wants addresses starting with 1 kids. On a desktop grinding 100,000 keys per second, a 2-character prefix like 1K has a search space of only 58 squared, or 3,364, that finishes in milliseconds. Extending to 4 prefix characters, roughly 1 kids, means 58 to the 4th, about 11 million combinations, which takes around a minute. 7 characters jumps to 58 to the 7th, about 2.2 trillion, stretching into months. At 9 characters, you need 58 to the 9th, which is roughly 7.4 times 10 to the 15th, on the order of hundreds of years. And 11 characters, like 1 kid's charity, pushes you to 58 to the 11th, about 2.5 times 10 to the 19th combinations. Millions of years longer than Homo sapiens has existed. You can run GPU farms or hire vanity pools. That's brute force for you. But every character you add is another factor of 58. That's why most vanity addresses you see in the wild are short, and why the elaborate ones were almost certainly generated by specialized hardware. So why did Vanity addresses fade? Two reasons. First, modern wallets are deterministic. A single seed phrase generates a tree of thousands of addresses. A Vanity key doesn't fit that tree. It's a one-off that needs its own separate backup, breaking the whole model. Second, privacy. If you post a memorable Vanity address publicly, everyone who pays you uses the same address. That links all those payments together on-chain and reveals your balance to anyone watching. What looked like branding is actually a privacy leak for you and for everyone who sends you Bitcoin. The cool factor isn't worth it. Vanity addresses are the only relic of Bitcoin's early years. Meet the paper wallet, a private key, and its address printed on paper. There were holiday editions, scratch-off stickers, tamper-evident foils, detachable stubs for fire or flood. Charming. And dangerously broken. Online generators have been backdoored for years. Users have had their coins stolen weeks, months, even years after printing. A paper wallet holds a single key, so it can integrate with deterministic wallets. To spend from it, you typically import the whole key into software, which exposes it, and reusing the address links every payment, same privacy problem as Vanity addresses. Modern best practice is two pieces. First, a recovery phrase, 12 to 24 English words that encode the seed for an entire deterministic key tree. Write it down once, it restores every address you'll ever use. Second, a hardware signing device, a purpose-built gadget that keeps keys offline and signs transactions in isolation. The keys never touch your computer. Bitcoin's user-facing tools have evolved from ink and dice to cryptographic hierarchies. The formats, the fads, and the failures we covered today map that evolution, from the brittle 5 to the robust seed phrase.